Assalamualaikum and good evening. We are from Group 3. We'll present the experiment 5, which is the bending moment. And these are our group members. Bending moment is a measure of bending effect that occur when an external force, which is the loading, is applied to a structural element at a given distance. A moment is a rotational force that occur when a force is applied perpendicularly to a point at a given distance. Below was the formula related to moment, which is M equal to Fd. F stands for force and D is the distance from point reference. For the direction of moment, the clockwise direction means it was out of the page or vector points up, and the counterclockwise indicates the direction was get in the page and vector points in going to down. The application of bending moment we can see for the design of timber rafters and the steel beams. For the design of timber rafters, the rafters roof exposed to external force, which is the wind and snow, that leads to bending moment. The timber beam's capacity must be greater than bending moment to support the system. For the next design, which is the steel beams, also apply the same concept of bending moment, whereas the steel beams carry the loads of timber beams that subjected to bending moment to occur. The objective of the experiment is to measure the bending moment of material when subjected to different loads at different distance. There are two scopes for this objective. The first one is the coverage of this study is the different distance measured between point reference and force from 50 mm to 900 mm that having the same weight of load for each reading. Reading 1 equal to 0 Newton, reading 2 10 Newton, reading 3 20 Newton, and reading 4 30 Newton. Next, the study consists of different weights of load that in distance of force are exerted on each hanger that affected the moment formed. The range weights of load used is between the 0 Newton to 15 Newton in any load hanger. The distance change will set up for P1 equal to 50 mm, P2 equal to 300 mm, P3 500 mm, and RB equal to 900 mm.
Next, I will talk about theory. In this experiment, we use beam to investigate bending moment. Beam is a structure with loads attached to it perpendicularly. So when a force is exerted on the beam, it will deform by bending because it is no more in equilibrium forces. There will be internal forces resisting external force, which is normal force, shearing force, and bending moment. Normal force is perpendicular force to the surface, which also means vertical force. Shearing force means tangential force to the surface, and bending moment is resistance against rotation, preventing the beam from bending. Bending moment is caused by vertical forces, which refers to load attached to the beam. This is the free body diagram of this experiment. The place that lever arm will be replaced by alphabet P and beam support is replaced by vertical and horizontal force of R. There will be three equilibrium involved: vertical force, horizontal force, and equilibrium of movement. Since it is in equilibrium forces, the summation of force and movement will be equals to 0, and we consider going up right hand side and also anti-clockwise direction are positive direction. As you can see, there is no horizontal forces other than RAX and RBX. Thus we can tell that forces at RAS equals to RBX. So we assume horizontal reaction does not occur as bending moment is caused by vertical forces. If we have cross section at P2 and separate the body, there will be shearing force. V will be going in opposite direction. For one body, V going upward and another body V going downward. So that when join the body back, the summation of V force will be 0.
Experiment setup. So for the experiment setup, these are the apparatus that we'll be using. First, we have the beam, and then accompanied by lever arm that we are labeled P1, P2, P3. Then we have lever ruler. Then we have load that range from 5 Newton to 10 Newton. That should be the methodology for part A. So step 1 a beam are divided into three parts by using lever arm. That is P1, P2, and P3. So the step 2, the distance of P1, P2, P3, and B from A are 50 millimeter, 300 millimeter, 450 millimeter, and 900 millimeter respectively. And also the length of the lever arm is 150 millimeter. Next, step 3. Adjust the beam using the spring balance until the liquid in the level are balanced, and then record the initial data of spring balance. Step 4. A load of 10 Newton are placed on the lever arm. So a load of 10 Newton are placed on all lever arm. That is P1, P2, P3. Step 5. Adjust the spring balance until the liquid in the level are balanced. So step 6, record the data of spring balance. And the last step, repeat step 4 to 6 but with added load 20 Newton to 30 Newton to all lever arm. So for part B almost the same. A beam are divided into three parts by using lever arm, P1, P2 and P3. So the distance of P1, P2, P3 and B from A are 50 millimeter, 300 millimeter, 450 millimeter and 900 millimeter respectively. The length of the lever arm is 150 millimeter. So step 3. Adjust the beam using the spring balance until the liquid in the lever are balanced, and then record the initial data of the spring balance. Step 4. Different loads are placed on each lever. P1 is 5 Newton, P2 is 5 Newton, and P3 is 10 Newton, as example. So step 5. Adjust the spring balance until the liquid in the level are balanced. Step 6. Record the data of spring balance. And the last step, repeat step 4 to 6, but with each hanger having different loads, ranging from 5 Newton to 10 Newton to 15 Newton. Next will be the results and discussion.
Result and discussion. At part A, we use constant load with different distance. The data is tabulated as shown in table 1 and 2. Distance A to P1, P2, P3, and B respectively is shown in free body diagram 1. Since reading of spring balance has zero error is not starting at 0 Newton, therefore we set reference point at 20 Newton. This is the example calculation at P1 equals to 10 Newton, P2 equals to 10 Newton, and P3 equals to 10 Newton, which is the yellow highlighted at table 2. The experimental bending moment is spring balance without zero error times lever arm of 150 millimeter, which is 24 times with 150 equals to 3600 Newton millimeter. Then at theoretical bending moment, by placing a moment at B with referring to free body diagram 1, we'll get the value of RA. Next, by taking the bending moment at C, solving for the left part as shown in free body diagram 2, we will get the value of MC, the bending movement at C. Same goes to part B. At part B, we use different load with different distance. The data is tabulated as shown in table 1 and 3. Distance A to P1, P2, P3, and B respectively is shown in free body diagram 1. The same calculation also apply in part B. Question 1. Any observation during experimental conducted? The spring balance reading increased with the increase in the value of applied load. Experimental value of bending movement also increased with the increase in the value of applied load. The increase in the bending movement value occurs due to the increase in load that causes the beam to physically bend downwards. Question 2. Comparison between the bending movement value obtained from the experimental and theoretical calculation. Provide justification for any differences. So in order to compare the bending moment value obtained from the experimental and the theoretical calculation, the percentage error is calculated by using the percentage error of the formula. The result of percentage error between experimental bending moment with its theoretical is tabulated as shown in Table 4 for Part 4, Table 4 for Part A, while Table 5 for Part B. From the Table 4 and 5,
For part A, we have plotted graph of experimental and theoretical bending moment versus constant load. The graph shows the bending moment is increasing as constant load increases. Theoretical value is higher than experimental value for all the data. For part B, we have plotted graph of experimental and theoretical bending moment versus different value. The graph is increasing graph. Also, theoretical value is higher than experimental value for all the data.
there are slightly difference between the experimental and theoretical bending movement, which are in the range of 3.08% to 10%. The difference of experimental value of the theoretical value is due to some errors that occur during the experiment. The error which might have occurred include parallax error, which is the reading were taken when eye are not positioned perpendicular to the measurements, marking which caused inaccurate reading at the spring balance, and the liquid in the level was not positioned at the center of the level. Number two, the random error is due to the environmental factor. The air movement in the lab will cause the load hanger to swing, which lead to inaccurate reading of spring balance as well.
For the conclusion, the purpose of this experiment was to examine the effects of applying various force to the beam at various distance. After that, the bending moment can be computed by exerting force on the beam. It is evident from the statistics that the bending moment grows with the load. Subsequently, the data observation reveals that the theoretical data exceeds the experimental data. This is a result of the possibility of random error occurring throughout the experiment. In summary, the experiment's goal has been achieved. For the possible errors and improvements, parallax error, the observer must keep his or her eye level perpendicular to the scale of the measuring devices at all times. It is possible to collect multiple sets of reading in order to acquire an average reading. For human error, the experiment was not correctly set up, since the load hanger may shift slightly when the loads are changed. We must confirm that the hanger and loads are properly placed. For the safety and precaution, for the laboratory safety, wear appropriate personal protective equipment, including lab coats, gloves, and closed-toe shoes. Tie back long hair and avoid wearing loose clothing and jewelry that could cause in equipment. For the steps, take the measurement reading with your eyes, perpendicular to the level ruler to the scale to minimize parallax error. Apply loads gradually and within the specified limits to prevent spring deformation and overloading. Conduct the experiment carefully to prevent any errors and injury. So for the reference, this is the reference that we study to make our report. That's all from us. Thank you.